job is in an organization called OLICO Maths Education. And we are completely passionate about making maths make sense for all South African learners. So we have, for our learners at primary school, a whole set of activities called maths clubs, where we play maths games in order to help people learn maths in a fun way. So because I want to warm you all up, we are going to play one of my favorite maths games. Okay, so I need a volunteer, and Shane, you sat too close to me, so you have to be my volunteer. But I promise you it's not scary. Alright, we'll start with the easy version of the game. I promise you I don't bite. Okay, what we're going to do is we're going to have our hands behind our back. We're going to start with just one hand, right? When we're more confident, we're going to go to two hands. I'm going to say 1, 2, 3, show. And when I say show, you're going to bring your hand up and you're going to show me however many fingers you want to. You can do 3, you can do 4, right? And I'm going to do the same. And then our competition with each other is we're going to add our number of fingers, and the first person to get the answer is the winner. Okay. 1, 2, 3, show. 6. Yes? Right now, thank you very much for being my volunteer. We won't make her stand up. You are all going to, with the person next to you, you need to stand up. With the person next to you, you're going to have your hand behind your back. And I think with your brave hands, you can do 2 hands, right? Are we ready? 1, 2, 3, show. 1, 2, 3, show. Let's go. We can bring up 2 hands, right? We want to have slightly bigger numbers for grade 9s, right? Yes. Bring up your 2 hands. First person to add them together and shout out the answer is the winner. Have you got it? Yes. So I'm going to give you another couple of minutes to try this. And then if that's starting to feel too easy for you, you are going to switch over to multiplication. And there you're going to bring up your fingers and then multiply the numbers together. All right. So do a few more with addition and then with multiplication as soon as you're getting the additions too easy, right? First person in your team to shout out the answer is the winner. Let's see who wins. Go. You don't have to wait for me to say 1, 2, 3, show. You say it to each other. not a bad idea. It will definitely help you if you know your times tables. So that's the work that I do. I spend quite a bit of time making up games for people to play, to help them learn their maths, and that's what I do for our primary school kids. For our high school learners, we run after-school classes at a number of schools, and those classes are based on both with tutors and computers. So we do that to support our learners in high school. From your uniform, I don't think that we are at your school. What school are you guys from? We're definitely not at your school. But the other thing that we do have for all high schools is we have a website, learn.olico.org, where we have grade 7, 8, and 9 maths videos and questions to help you. And the other thing that we have is we run a WhatsApp hotline, and particularly now in preparing for exams, and if you just WhatsApp hi to that number, you can get some help in preparing for your exams, some questions. So those are what we work with our high school learners. And as I say, grade 9 is my favorite grade to work with. We've got a lot of grade 9s on our program. And it really is the nicest grade. You're starting to get into some real mathematics, but you're hopefully also starting to really take it seriously because you want to continue with mathematics into grade 10, 11, and 12, which opens all kinds of doors for you. So that's a little bit about me and what I do. But now, let's get into some ideas in mathematics. So, I would like you to add up all the numbers, the whole numbers from 1 to 100. In other words, 1 plus 2 plus 3 plus 4 plus 5, right? Yes. All the way to 100. And I'm going to give you 10 seconds to do that. Okay? Ready, steady, go. Okay, who has the answer? No one. Okay, I'm going to tell you a little story. And it's a story about a mathematician whose name was Carl Friedrich Gauss. And Carl Friedrich Gauss, when he was a little 6-year-old boy, was sitting in his classroom. And his maths teacher wanted to get on with her marking and didn't actually want to be disturbed by her learners. And so the maths teacher said to her learners, now remember they're 6 years old, right? She said to them, I want you to do this. Add up all the numbers from 1 to 100, the whole numbers. In other words, I want you to do 1 plus 2 plus 3, right? And the teacher thought, it's going to take them ages. I'm going to have plenty of time to finish my marking. But little Carl Friedrich Gauss took 10 seconds and he gave the answer. How did he do it? Well, he did what we do in mathematics. And instead of just going plod, 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 he looked and thought, can I see any patterns in this thing? And what he saw is, if I write it down backwards, right? I go from 1 to 100 forwards and 100 to 1 backwards. What's 1 plus 100? 109. What's 2 plus 99? 109. What's 3 plus 98? 101. What's 99 plus 2? 109. Can you see what Gauss was seeing? Yes. He saw, I've got 101, 101, 101, 101, 101, right? All the way along. How many of them did he have? 100 of them, right? Because there are 100 numbers here, so 101, 101, there are 100 of them. So what is the total that he would get? He would get 100 times 101. Now that's a very easy calculation to do, right? Yes. We all know how to multiply by 100. We just shove the zeros on the end, right? Yes. And then he said, but that isn't my final answer, right? Because the teacher only wanted me to do one of them, right? And I've gone from 1 to 100 and 100 to 1, so I've got 2 of them. So I must divide it by 2, so my answer is 5,050. 10 seconds, he's done. And that was because he was doing what mathematicians do and noticed patterns that enabled him to do things quickly. So, and that was at age 6, eh? As you can imagine, somebody like him, there is this, our beautiful Carl Friedrich Gauss. You can see he lived quite a long while ago. Very famous mathematician. So from his age 6, where he did that quick little puzzle, he went on to much bigger and greater things. And he did all sorts of interesting work in mathematics, non-Euclidean geometry, blah, blah, blah. But one of the things that he did, which I'll just show you very quickly, is, you know how to solve equations, right? Yes? Yes? You solve equations, yes? Well, he invented a quick way of solving these kind of equations, which are much more difficult than the equations you've got, right? Because in this equation we've got x, y, and z. And what he invented was a little way of turning them into what we call a matrix, and then doing a series of moves on the matrix which involve adding or subtracting one row to the other, that eventually just popped out the answer very nicely. So I'm not going to go through the details of this. When you get to second year university maths, you'll learn how to do this. But this is the kind of invention that mathematicians come up with, right? They start to look at what they're doing and find ways that are better able to do it. So I'm going to take you on to another mathematician. And this is going to, this man, his name is George Cantor, and he's particularly famous for what he did in mathematics in thinking about infinity. Now, do you know what I mean when I say infinity? You know, we say like there are infinitely many things, right? It means we can't count them, right? It just goes on forever and ever. And that we know with our numbers, right? There's no stopping point for our numbers. They go on forever and ever and ever. This idea of infinity in mathematics is probably one of the most kind of mind-blowing and complicated ideas in mathematics. And when Cantor started thinking about it, and he started coming up with some of the ideas, he totally revolutionized the way in which we think and allowed for the development of some of the most powerful mathematics that's used in engineering, etc. So I'm going to give you a little taste of thinking about infinity in Cantor's way, right? Yes. And I'm warning you right now, you're going to think that I'm talking rubbish by the end of this because it is something that generally blows your mind. So I want you to just talk to the person next to you and tell me, where do you have more numbers? If you've got the whole numbers, so you just go 0, 1, 2, 3, 4, etc. Or if you include the negative numbers as well. Where are there more numbers? Speak to the person next to you. Which is bigger set? Just 0, 1, 2, 3 upwards? Or when you include the negative integers as well? Where do you think you've got more numbers? Where do you think? Right there. Where do you think you've got more numbers? Where do you think? Okay, so I'm seeing quite a few people are saying, yeah, obviously it's the integers, right? Yes. Okay. So now here where you need to hold on to your head, right? Because this is what Cantor managed to tell us. They are the same number in both of those. Now that doesn't make any sense, does it, right? Can't be, right? Let's go with how Cantor argued this. How do I tell if I've got the same number of things here as I've got there? Well, obviously I can count them, right? But another way I could do is say, if I can match up each person with a sweet, so that each person just has one sweet, then I know that I've got the same number of sweets as I've got people. Yes. Okay, so now I need you to all agree with me. Is that true? Yes. If I can match up 1 to 1, then they're definitely the same number. Yes. All right. So now, here's Cantor at work. He said, let's have a look at those integers. We've got a 0. We've got all the negatives. And we've got all the positives. Now, if I can match all of those 1 to 1 with the positive numbers, then they are the same amount, right? Yes. Okay. So watch me match. This is actually Cantor doing it, not me, but I'm just copying Cantor. Cantor said, let's take the 0, that's in the integers, and we'll map it to the 0, right? In the whole numbers, right? So it's got a partner. Let us go with our negative numbers. What I'm going to do to find a match for my negative numbers is I'm just going to multiply them by -2. So what's -1 times -2? Negative times negative is? Positive. So it's +2, right? Yes. What's -2 times -2? Positive. You're getting it, right? Yes. So that's the match I've made. So can you see I'm matching every negative has a friend, and their friend is what kind of number? It's positive, but what kind of positive number? Even number, right? Yes. So every negative is matching very nicely to an even number. What about the positive numbers in my set of integers? I am going to match them by multiplying them by 2 and subtracting 1. So what's 1 times 2? 2. Minus 1? 1. Right. 2 times 2? 4. Minus 1? 3. Okay? So that way I can match them up, right? And they're matching up with the odd numbers, right? So can you see I have managed to match every one of these numbers with every one of those numbers. Every one has a direct match. The negatives match to the evens, the positives match to the odds, and 0 matches to 0. So just like the people on the sweets, there are the same number of numbers in both of those sets. Now that should blow your mind, right? Yes. Because you kind of know, but there are all these negative numbers that are in addition, right? Yes. Why is it working out like this? It's working out because of these dots. It's because of infinity. Because there is no stopping these numbers. So because of that, that's why this thing works. And that was the major breakthrough that Cantor made, right? And this is the kind of thing where what you're dealing with at school in the maths is all preparation for some of this stuff. But when you start getting into these orders of infinity and thinking about infinity, that's when the magic of mathematics really starts to unlock, and where the mathematics then became useful in calculus, that is then used everywhere in engineering, in computers, etc. So giving you a little bit of a flavor of that stuff. All right, so that's that story. Another story about a mathematician, and this is one now you're going to have a nice, interesting debate about. This man, his name's John Nash, and he was a mathematician who actually only died 10 years ago, so we're getting a bit closer to now. And the area of maths he worked on was called game theory. And game theory is used a lot in economics, but it is used very much in all sorts of other places. And if you have any option, there's a book and a movie called A Beautiful Mind, which is about this guy and what happened to him. So it's a really interesting one to look at. But here is one of the famous problems in game theory that started off the development of game theory. So you can see this is quite different from the maths you've been doing at school, but it is a very important part. So this is just a little taster of game theory. So I'm going to ask you again to talk to the person next to you. So the thing is called a prisoner's dilemma, right? So what happens is, okay, so you're all in your pairs, right? And you've committed a crime, right? Now, please do not believe, I'm not trying to promote committing crime, right? That is not what I'm suggesting with this. This is just the famous example, right? So each of you in your pairs, both of you committed a crime, right? I'm the cop, I caught you, but I don't have quite enough evidence to go anywhere with this. And what happens is, I've got you both in separate interrogation rooms, right? If you both remain silent, I'll just have the little bit of evidence I've got, and so I'll only be able to put you in jail for 1 year each, right? Now, if you're in your separate rooms, right, and this person says to me, he did it, this person will go free, getting nothing. And that person will be put in jail for 3 years. If this person says he did it, and that person says she did it, you will both get 2 years. You understand? Yes. So if you both stay quiet, 1 year each. If you say the other person did it and they say nothing, you go free, they get 3 years. And if you both say the other person did it, you both get 2 years. Right? Now what I want you to imagine is you are sitting in those interrogation rooms. You can't speak to the other person, right? You don't know if your friend is going to tell on you or not. What is your best strategy? What is the best strategy that you should do? Should you keep quiet, or should you say he did it? Okay, now don't answer me, right? All right. So I want you with the person next to you, right? Don't talk to them yet, right? Imagine you are the two people sitting in those interrogation rooms, okay? Make a decision for yourself about whether you are keeping quiet or, right? So this is the signals we're going to use. You're either keeping quiet or you're going to say, he did it, she did it, right? Think for yourself, right? And then when I say, so, and you've got your partner, right? Everybody got a partner, yeah? When I say, go, you're going to show us what you did, and then we're going to figure out who got 3 years, who got 2 years, who got 1 year. Okay? Right? So just give yourself a little bit of thought. Right? You're sitting in that interrogation room. Are you keeping silence, or are you going to talk and say, he did it, she did it? Make a decision for yourself. Don't talk to the person next to you. Don't talk to the person next to you because you don't have any option of talking to the other prisoner. Think it through for yourself. Okay, has everybody made a decision? Yes. All right. I'm going to go 1, 2, 3, go. And when, as I say go, you have to immediately show whether you are keeping quiet or talking, right? You can't change your mind halfway. When I say 1, 2, 3, go, we see, and then we see who gets how much, right? Yes. Ready? 1, 2, 3, go. All right, so let's see. How many of you got only 1 year in prison? That's if both of you kept quiet. Okay. How many of you are free? In other words, you talked and your friend kept quiet. How many of you got 3 years? Oh, you don't have nice friends, do you, right? And then how many of you were both nasty and got 2 years? Okay. So, this prisoner's dilemma is a classic problem in game theory. And I'm not going to go into all the details of it. But basically, the story is that it is always better, the best option for you is always going to be to talk.
Yes.
Because, let's look at it, right? I'm going to be prisoner A, right?
Yes.
If my friend, or maybe not so friendly friend, but if my friend, prisoner B, says nothing, right? They stay silent. Which is it, if they don't say anything, which is better for me to do? Obviously better for me to say, he did it, right?
Yes.
Because then I'm going free and he goes to jail, right?
Yes.
If I stay silent, I get 1 year in jail, right? So if my friend stays silent, the best option for me is definitely to say, he did it, right?
Yes.
What if my friend decides to say she did it? What's my best option? I definitely don't want to stay silent because then I'm going to jail for 3 years. I want to say, he did it too, and then I only get 3 years. So if I'm thinking rationally and logically, I should always say he did, because that's the way I'll come out with a better option. And this is what game theory started to work with. Okay, this is going on beyond. And this kind of stuff applies to all sorts of things. About, I mean, this is just the beginning of game theory, but it applies to stuff like, how do businesses work with each other or against each other? Do I raise my prices or lower them? And this was mathematics and worked through to this kind of branch of mathematics called game theory that has got massive applications in all kinds of areas of life. Okay, so I want to just move on and show you a few other things, but this is going to go quite quickly. So here is a much more recent mathematician. She's an American woman, and what she developed was a way of, and this is a very powerful use of mathematics, which is in being able to create graphics and ways of representing objects. And I'm not going to pretend that I can even begin to understand what she was doing here, right? But you can see in all of that there is a whole lot of stuff with your geometry and work with geometry and curves, etc., to be able to reflect things through various processes to create images. And this is another area where mathematics is incredibly powerful. And what you will see, I mean, basically if you think about computers, what are computers based on? Mathematics, right? You've done some graphs in your life, right? Your graphs are just two-dimensional graphs. But when you go further, you have three-dimensional graphs. And three-dimensional graphs are when you can create the objects that get created on a computer screen. That then, if you're playing any kind of games and that sort of thing, those things get moved around, etc. All of that is done by the coordinate system of 3D graphs. So that is the kind of power. So I'll just show you some of these 3D graphs. There's a point, 1, 1, 2. The x is 1, the y is 1, and the z is 1. So you've got a little point in space. You can then have equations like z equals 2, which gives you a plane in space. Y is 1, another plane in space. And then you've got equations like this thing that create a pretty beautiful kind of paraboloid in space. So all of these things, you can picture how this might happen, right? Take away the axes, you've got the pictures that appear on a computer screen that can then be moved around and used to create computer games. So, I'm hoping that with some of that, I've given you a little bit of a taste of the mathematics that you're doing at school is building up to all of this stuff, to places where you can actually work with game theory to understand economics and how it works in the real world, to working with graphs to be able to create computer graphics and move pictures around the computer screen, to have the knowledge of infinity that enables you to understand calculus and how it will work in engineering applications. So I'm not going to go through all of this in detail, but I did just want to point this out to you, especially seeing you're in grade 9, that there are some really, the options are open to you if you take mathematics through to matric are huge, right? And so this is just a few of the ideas and places where you can go into careers that require mathematics as the basis. So earth and environmental sciences, engineering and construction, IT, information technology and computers, finance and commerce, another one requiring mathematics. Your medicines and your health sciences require your mathematics for matric. And of course, teaching and research is another area that requires. And I would really suggest that you have a look at some of these places now before you make your choice for grade 10 as to what you're going to go on with. So there's this samf.ac.za, it's the South African Maths Foundation. They've got a really nice booklet on careers in mathematics. And then the NSTF.org.za, and I think that you've got some of their papers with you on your desk, have a really lovely booklet about career fields in science and mathematics, which is so worth going through. There are careers in there that I have never even heard of, and it really opens your mind to what the possibilities might be for you. And my encouragement to you is to say, you know, at the beginning there were not many people who said maths was their favorite. And part of the thing with maths is that it actually takes consistent work to be able to do it. You can't just come to it 3 seconds before the exam and expect everything to come to you. But here are 2 quotes from very famous mathematicians who made it all the way to the top of mathematics. Albert Einstein, you heard of him? What did he say? It's not that I am so smart, it's just that I stay with problems longer. And that is really true, right? It's saying, don't just give up when the math seems a little bit hard. Be an Albert Einstein and say, I'm going to sit with this until I really get it. And then Paul Helmers, another famous mathematician, you might not have heard of him, is, and I've made a mistake there, the only way to learn mathematics is to do mathematics. And that is what my message I want to leave you with today, is there's all sorts of exciting bits in the world that open up to you with mathematics. There's so much more beyond school mathematics that then has these applications into really exciting fields of work. And all it takes to do mathematics is to sit with the problems a bit longer and to make sure that you dedicate yourself to doing the practice required to get on top of it. And once you do that, mathematics becomes easy. So that's it for me, and I don't know if you wanted to give them anything on your STEM exercise.